In today's class, we are going to find out the energy of a simple harmonic oscillator. The final result that we are actually looking for is that the energy of the oscillator is directly proportional to the amplitude square. Now, when you are, talking about energy, we are also talking about intensity. That means a very important relation that in optics we observe that is nothing but intensity is directly proportional to amplitude square. So in this case as well, if we can find out that energy is proportional to amplitude square, that it means obviously that the intensity is proportional to amplitude square. Now, what amplitude are we talking about? We have already, seen this example of a pendulum, and when we are talking about the oscillations of the pendulum, the maximum oscillation on either side will actually be your amplitude. So this would be your amplitude. So the example of a simple harmonic oscillator that we are going to talk about is a spring box system. So, if you're talking about a spring system, we do have the restoring force acting. Okay. So what we are going to say is, let's say we have got a box which is connected with a spring and we are pulling it and it gets displaced by a distance x. Now, this will actually oscillate to and fro, giving our simple harmonic motion. Let's find out what's the energy that is stored in this simple harmonic oscillator. So, by definition, which we have seen before, that the acceleration of a simple harmonic oscillator is directly proportional to the displacement. But then the displacement is in the opposite direction to the acceleration. That means that if I'm pulling this block in this direction and then leaving it, the acceleration is going to be in the opposite direction. So we can say that the acceleration of the simple harmonic oscillator is proportional to the negative displacement. So if we remove this proportionality sign, let me just put an equality there. I can replace it with a constant, and that constant is nothing but we usually use it as omega square, and then the displacement may be x. So this is the acceleration of the simple harmonic oscillator that we have, and we are going to use this relation to derive our final result. So it's very important. We're basically going to start with this. So let's mark this as a relation 1, and this omega square is our constant. Now, the restoring force or any kind of force is more or less mass into acceleration, and we have got written restoring forces RF. Now, on top, we have found out what is our acceleration, that's minus omega square x. So let me just write it down as minus m omega square x. So that's our restoring force now. Very important relation. If you recall Hooke's law, if you can recall Hooke's law, we know that the force is proportional to the displacement, and the displacement is in the opposite direction to the restoring force. So we can put a minus sign, or we can say it is equal to minus kx. Now, what is this k? The form of k would be this particular term. So x is there, minus is there, so it is m omega square. So k is nothing but m omega square. Okay, so you have to remember this relation, but we are getting the form of k that we should have in such system. Now let's define work done. Okay, and we know that work done to displace a particle from x to x plus dx against the restoring force is actually stored in the form of potential energy. So if we denote potential energy by U, it is equivalent to the work done, which is equal to force into displacement. So let's see what are the relations we have. So the force that we have now is this particular relation. Okay, we can just consider the magnitude here. So let's say I have got a small uh, potential energy, let's say it is du, and this force would be nothing but m omega square x into, okay, we have got the displacement again. So this displacement is a small displacement, so I can write it down as dx, because work done to displace a particle from x to x plus dx, so the displacement is dx. So this is your displacement. What is the force? Minus m omega square x. We've just taken the magnitude because we're considering potential energy. Now, if you want to find out the total potential energy, we have to integrate it. So if you integrate du, we can have u. And on this side, we need to integrate this, and it will be nothing but m omega square x dx. So m omega square is a constant. We can just take it out. This is m omega square into x dx would be nothing but x square divided by 2. And we are actually having a definite upper limit and lower limit. We're displacing it from x to dx. Okay, so we can keep it to be some value. So what we can do now is, let me just take the, so this is our potential energy. What we can do now is, maybe you can just write it down. U is equal to minus m omega square x square divided by 2. So that's the potential energy that we have. Now let's find out what's the kinetic energy. Now for kinetic energy, what we can do is we can write it down as kinetic energy is equal to half mx dot square, right? But we know x dot is x. You have to know what is the form of x. Now if you're considering a simple harmonic motion, okay, if you're considering a simple harmonic motion, you can write down the displacement in this form. We have done it before as well, discussed it in detail. X is equal to a sine omega t, because we are talking about a simple harmonic motion, so it will have a sine component or a cos component. So let's say x is equal to a sine omega t. So that means if I want to find out what is my x dot, I can simply differentiate this term with respect to t. Okay, dx dt is x dot, so I can simply write it down as a, and if you differentiate sine omega t, you are going to get omega cos of omega t, right? Now, we know the relation between sine and cos. If you remember, sine square theta plus cos square theta is equal to 1. So that means what you can do is cos square theta, we can use this relation, is equal to 1 minus sine square theta, or we can say that cos of theta is equal to root over 1 minus sine square theta, right? This is the relation that is known to us. So we're going to use it here, and let's see what we are going to get. We can simply write it down as equal to a omega, and in place of cos omega t, I can write it down as root over, my theta is omega t here, so it will be 1 minus sine square omega t. Now you can check here. If you look here, x is equal to a sine omega t. It simply means that sine of omega t is equal to x divided by a. So we can use it here. So we can simply write it down as a omega root over 1 minus, this is squared, so it would be sine square omega t would be nothing but x squared divided by a square. So if we take this a square out of the root, we can just simply have it as a. So it will be a omega divided by a. We can take the LCM, and this term would be nothing but, we can go here. So that would be a square minus x square. So a gets cancelled, and I simply get omega root over a square minus x square. So what is a? A is our amplitude. Now, if you look here, okay, we have got this relation for x dot, and we have kinetic energy k is equal to half mx dot. So let's modify that relation. That means we can write down, therefore, kinetic energy is equal to half m, and in place of x dot square, we can take this relation. So it would be nothing but omega root over a square minus x square. Dot square is there, so I square of this. Okay, let's simplify this a bit. So it will be half m omega square, and we can take this term out of the root. This would be a square minus x. Right, so where A is the amplitude. Now, if you look into the potential energy, this is our potential energy, and this is our kinetic energy. So if we actually want to find out the total energy, let's mark this as expression 3. Now what we're going to do is we are going to check for the total energy. So let's write it down, the total energy. So, total energy, let's mark it as E is equal to nothing but potential energy plus kinetic energy will actually cancel out. And finally, the result that I will have is half m omega square A square. Okay. So just taking the, we know energy, kinetic energy, potential energy, all are scalar quantities. The minus sign was because it was a force was actually considered to be a vector quantity. But in the final result, we can take it to be just a scalar. So we're just considering the magnitude here. So this term and this term will get cancelled out. And the result I have is energy is equal to half m omega square A square. Now mass of the system is constant. Omega is the frequency, which is again a constant. So it obviously means that the energy is directly proportional to the amplitude square. So this is the result that we have. And if the question is, what is the energy of a simple harmonic oscillator? You would be simply writing it as half m omega square A square. That's the total energy. And that means that the energy is proportional to the amplitude square.